So differentiation is finding the gradient of a curve, or rather finding an expression for the gradient of a curve. And in first year maths, you did a lot of that with just polynomials. So things of the form, x squared plus 3x plus 2 is a polynomial, or a cubic, or a quartic, or quintic. You would be asked to differentiate that. But sometimes we'll have more complicated expressions that are more difficult to differentiate. And that's where something like the chain rule comes in to speed up those types of questions. So, for example, we'll start with e.g. And this here means differentiate with respect to x. d dx means differentiate what I write next to that with respect to x. d dx of 2x plus 4 squared. So what you could do with this is just multiply out the brackets. So that becomes d dx of 4x squared plus 16x plus 16. And it's asking us to differentiate each of those terms with respect to x equals 8x plus 16. So you might or might not have seen that differential operator before. You do actually need to know it. It could come up in an exam, although it is unlikely. I haven't seen the notation in an exam, but on a lot of specs it is specifically mentioned. So d dx means differentiate what it's attached to with respect to x. But it becomes a lot more difficult, or rather time consuming, if I ask you to differentiate 2x plus 4, say to the power of 20, because now we've got 20 brackets to multiply out. So in such cases, what we're going to do is do a substitution. So I'll write some steps out for you. If you want to copy these down, brilliant. If not, don't worry. So step 1, let u equal the innermost expression, or in this case, the bit in the bracket. So the bit that's most deeply wrapped in another function. So we've got 2x plus 4, and we've wrapped around it a power of 20. So let's do that. Let u equal 2x plus 4. And that means now that we're going to differentiate this, but we're replacing that with u. So I'm going to go back to this line here and rewrite it as y equals 2x plus 4 to the power of 20. And that'll help things out. That'll make it easier to write. So if y equals that, so the challenge here is to find dy by dx. So if u equals 2x plus 4, now we've got y equals u to the power of 20. So we've done a substitution, u equals 2x plus 4. So y equals u to the power of 20. Next bit, what we're going to do, step 2, find du by dx and dy by du. So basically differentiate each of these two expressions. So du by dx equals just 2. If I differentiate that du by dx, I just get 2. And dy by du equals 20 u to the power of 19. So differentiate that, 20 u to the power of 19. And this is more proof of why the chain rule works. I'm going to show you an easier, quicker way in order to implement this a little bit later. But for now, let's just do it this way. Do it formally. So step 3, dy by dx equals du by dx times dy by du. And to convince yourself that this is true, imagine, it's not a fraction, but imagine this as a fraction. In such a case, the du's cancel to give dy on top, dx on the bottom, to give dy by dx. So basically, the next step is to multiply these two expressions that we've gained together. So dy by dx equals du by dx times dy by du, 20u to the power of 19, equals 40, and in this case u was 2x plus 4 to the power of 19, and we're done. So that's the formal method and why it works. But I'm quickly going to say, as I did before, quickly going to say again that there is a better way of thinking about this. So let's go back up to the original question, which was differentiate 2x plus 4 to the power of 20. And the way I imagine this working, I imagine somebody stood outside the bracket and he can't see what's in the bracket. All he sees is bracket to the power of 20. So the best he can do is differentiate it as a bracket. So a bracket to the power of 20 is 20, whatever's in the bracket, to the power of 19. Not being satisfied with what he's done, he then looks in the bracket and sees that it's 2x plus 4 and multiplies by its differential. Remember, we are differentiating like that. So equals 40, 2x plus 4 to the power of 19. And that just eliminates the need for the formal method, and it's actually expected, and in fact encouraged, that you'd do it this way. So let's do another. Dx of x cubed plus 6x to the power of 5. So again, this bloke here, all he sees is bracket to the power of 5. So he differentiates it as best he can. 5 bracket to the power of 4. Looks in the bracket, sees that there's x cubed plus 6x, and multiplies by its differential, 3x squared plus 6, like that. Equals, and to be honest, I'm not convinced we can write that any simpler. That's as good as we're going to get it. 5 x cubed plus 6x to the 4 times the differential of the bracket, which is 3x squared plus 6. Let's do another. Dx of 5x squared plus 6 to the power of 20. So differentiate the bracket as a whole. 20 bracket to the power of 19 times the differential of the bracket, which is 10x. Remembering 5x squared plus 6 was in the bracket. Equals 20 times 10 is 200, not 30 as I was about to write. 200x 5x squared plus 6 to the power of 19. So that's basically the chain rule. Differentiate the expression as a whole without looking in the bracket, then times by the differential of what's in the bracket. And that's basically what this method does. So this here is you differentiating the bracket as a whole, 20 bracket to the 19. Then this is you timesing by the differential of what's in the bracket. So this quick method matches up entirely with the substitution method, but it's just a little bit quicker, a bit less formal. And as I say, it's encouraged to do it like that. So now let's do some standard differentials. So standard, do it in black as keep the color code going. Standard differentials. So the differential, and these are just ones that you have to learn. the differential of e to the x is just itself. And that's one you've just got to learn and accept. E to the x differentiates to itself. The differential of natural log of x is 1 over x. Again, one you've just got to learn and accept. And differentiating sine and cos, sine x differentiates to cos x. If we differentiate it again, we get minus sine x. Differentiate again, we get minus cos of x. Differentiate again, we get back to the start. So that's basically some new differentials that we've got. And furthermore, in the formula sheet, you're given a load more standard differentials to learn as well. Sorry, not to learn. You're just giving them so you don't actually need to learn these. So there's a few more that you're given. So the differential, forget about the k for now, the differential of tan x is sec squared x. The differential of sec x is sec x tan x. Cot x differentiates to minus cosec squared x. Cosec x differentiates to that. And we'll be able to prove some of these after the lesson next week. So for now, it's just a case of accepting that they're there. So now let's do a few chain rule questions involving these standard differentials. So let's do the differential of e to the 2x. So the idea we could do a substitution, like we did before, using the formal method, where we let u equal 2x, because there's not explicitly a bracket drawn there, but if there was, it would be around the 2x. So step 1, going back up there, let u equal the innermost expression, well, the thing most deeply wrapped there is the 2x. So imagine the bloke standing outside the e to the 2x. He can't see through the brackets that I've drawn in there. All he can see is e to the power of something. So the answer, when we differentiate it, has to be e to the power of something, whatever that thing is. Haven't looked inside the bracket, so I don't know yet. So now let's look in the bracket and times by its differential equals 2 e to the 2x. Try a different one. Dx of, let's say, log, natural log of x squared plus 3. So can't see through brackets, so we just got log of something. So the differential of log of something, as we can see here, is 1 over whatever that thing is. So log of whatever's in the bracket differentiates to 1 over whatever's in the bracket. Haven't looked in yet, so I don't know. But once we're done, we multiply by the differential of the bracket. So we'll look inside, x squared plus 3 was in there, and times by its differential, which is 2x, equals 2x over x squared plus 3. And another, let's differentiate sine of e to the x plus natural log of x. Looking a bit more complicated here, but I assure you it's relatively straightforward. So we're differentiating sine of something. Let's not look in the bracket. Sine of something differentiates to cos of whatever's in the bracket. Don't know what it is yet, I haven't looked. Now let's take a look in the bracket. What's in the bracket is e to the x plus natural log of x. And now we've looked in the bracket, we're going to times by its differential, times, well, differentiating that, e to the x plus 1 over x, log x differentiates to 1 over x. And let's just tidy that up a little bit, equals e to the x plus 1 over x times cos of e to the x plus log x. And that's basically the trick. Just don't look in the bracket, differentiate the thing as a whole, then times by the differential. Once we've looked in the bracket, times by the differential of the bracket. So we'll do a few more complicated trig ones in a second, but I just want to do a few, just want to explain when this rule is applicable. So we know the rule now. So this rule is only applicable when you've got functions of functions. So I'll write that down. So the rule is only applicable for functions wrapped in other functions. So what I mean by that, let's say we've got a function, x squared plus 5, and I'm going to wrap it in another function. I'm going to raise it to the power of 10. That's a function wrapped inside another function. Let's say I've got sine x, and I wrap it in another function. I decide to wrap it in a natural log. Again, that's a function of a function. We've wrapped a function around a function. One where it's not applicable, x squared cos x. So what I haven't done there is wrapped a function around another function. I've taken two separate functions and I've multiplied them together. The chain rule doesn't apply there. We can't use the chain rule because that's not a function of a function. It's two separate functions multiplied together. So it doesn't apply. That's a product of two functions. And we differentiate that using the product rule, which I do next week. So let's do a few exercises on this. So I'll just get a couple of questions ready. So I'll give you a moment to have a go at those. See if you can have a go at those. Take a few minutes. So this first one there aren't any brackets drawn, but let's wrap some brackets around it. So 2e to the 3t. So let's differentiate the full thing without looking inside the bracket. So 2e to the 3t differentiates to 2e to the 3t, differentiates to itself. And now that we've looked in the bracket, times by its differential, which is 3, equals 6e to the 3t. Part B. First write it in a differentiable format, 4t minus 1 to the power of a half. And if we differentiate that, we get, so let's not look inside the bracket, we just get a half bracket to the power of minus 1/2 times the differential of the bracket, which is 4, equals 2 4t minus 1 to the minus 1/2. When we simplify, 5 log 2t. Well, we know it's 5 times something. So before, this can be considered not the product of two functions, because 5 is a constant. So if we ignore the 5 for now, and we are allowed to ignore constants and put them in later, just like we did here. So log of 2t differentiates to 1 over 2t, provided we don't look in the bracket. So 5 lots of that becomes 5 over 2t. Multiply by the differential of the innermost part, the bit in the bracket, times 2, which gives us just 5 over t. And part D, times by the power, take 1 from the power, times by the differential of the bracket, which is minus 3, equals minus 9 over 2, 8 minus 3t to the power of a half. So putting this into practice now, we'll have some more in-context questions. Let's have a look at each of these. Find the value of x for which the differential takes the value indicated in each case. So we're looking for the value of x in this expression that would make the gradient function equal to 2. So in this case, let's find the gradient function, differentiate that first. So f dash x equals, well, before we can do that, it helps to write it in a differentiable form, 3x plus 15 to the power of a half. Have a go at that, take a moment, differentiate it. I'll finish it off in just a moment. So don't look inside the bracket, just multiply by a half, take 1 from the power. So we get a half of 4 is 2, 3x plus 15 to the minus 1/2, multiply by the differential of the bracket, which is 3, equals 6 lots of 3x plus 15 to the minus 1/2. And we want the value of x, which makes the gradient function here, equal to 2. So we're saying that this is equal to 2. It's not asking us to sub 2 in. It's asking us to find the value of x, which makes the gradient function equal to 2. The gradient function equal to 2. So now you've got an equation to solve. Now, in order to solve this, I think it's much easier to write it in non-index format, i.e. rather than writing as power of minus a half, we know that means the reciprocal, the minus means reciprocal, of the square root, power half means square root, so that becomes 6 over root of 3x plus 15 equals 2. Multiply by that, divide by 2. We get 3 from dividing by 2 equals root 3x plus 15. Square both sides. 9 equals 3x plus 15, which means that 3x equals minus 6, which means that x equals minus 2 is the answer. So have a go at the next one. And we want the gradient function to equal 5. So I'll start you off with it, then pause again. So differentiating that, f dash x equals, well, we know how to readily differentiate that without any rules whatsoever. That just becomes 2x. Take, then the differential of log of a bracket becomes 1 over whatever's in that bracket, times the differential, now that we look inside the bracket, times the differential of what's in the bracket, which is just 1. So it just becomes 1 over x minus 2 times 1. And we won't bother writing it, times 1. And we want the gradient function to equal 5. So now, if we times everything by x minus 2, both sides 2x, x minus 2, take 1, equals 5, x minus 2, and it looks like we've got a quadratic to solve. Have a go at solving that quadratic. So I'm going to take the easy way out here. It doesn't ask for full working or detailed reasoning. So I'm just going to solve it on the calculator. Polynomial of degree 2, 2x squared minus 9x minus 9. Type that in wrong, should be plus 9. Is 3. Or 3 over 2. And there are two answers. So let's have a look at another one. Let's have a look at some involving stationary points now. So again, all we're doing is putting these into context. Relatively straightforward as the chain rule. The hard part is applying it. So find the coordinates of any stationary points on each curve. So before we looked at where the gradient was equal to 2 and 5. Stationary points occur when the gradient is 0. Go for it. Have a go at some of those and I'll pick it up in a couple of minutes. I'll give you a chance to get started. So differentiating the first one, dy by dx equals 5 bracket to the power of 4 times the differential of the bracket, which is 2, equals 10 2x minus 3 to the power of 4. And we want the gradient, the differential, to be 0. So the value of x that makes this expression equal to 0 would occur when 2x minus 3 is equal to 0, i.e. when x equals 3 over 2. But it did ask for the coordinates. All we've found so far is the x coordinate. We need to sub it back into the original expression and find what the y coordinate is going to be. So let x equal 3 over 2, which implies, and we can see because the bracket is the same form of that one, that's just going to be 0. Y equals 0. Therefore, conclude stationary points at 3 over 2 is the x coordinate and the y coordinate is 0. Part B. Find the coordinates of any stationary points on each curve. So I'll give you a moment on that one again. I'll pick it up in a minute. Okay, differentiating that, dy by dx equals 3 bracket to the power of 2 times the differential of the bracket, which is equal to 6x x squared minus 4 squared, which we want to be equal to 0 because we're talking about stationary points here. So that the stationary points here occur when 6x equals 0, or when x squared minus 4 equals 0. Well, we know that this one occurs when x equals 0, quite an easy one to solve. Or when x squared equals 4, which means that x equals plus or minus 2. So we've actually got 3 stationary points to find now. So the function was y equals x squared minus 4 all cubed. So let x equal 0, which means that y equals 0 squared minus 4 cubed equals minus 64. X equals 2 means that y equals x squared minus 4 cubed, which is 0. X equals minus 2 is going to give the same result, but let's show the working. Y equals, again, minus 2 squared minus 4 cubed, which again is 0. So therefore, we've got stationary points at x equals 0, y equals minus 64, x equals 2, y equals 0, and x equals minus 2, y equals 0. So let's do another couple of examples. Moving away from stationary points now. Find an equation for the normal to each curve at the point with the given x coordinate. So find the gradient, get a point on the line, and supplement the straight line equation. Have a go at those two. I'll give you a couple of minutes to get started. Then I'll start going through part A. Right, so the differential of the first dy by dx equals, well, e to the something differentiates to e to the something, whatever that thing is, then times by the differential of what's in the bracket, which in this case, don't forget that it's minus 2x, which is equal to minus 2x e to the power of 4 minus x squared. So now we want to find the gradient. Let x equal minus 2, which means that dy by dx equals minus 2. I forgot to explicitly state that minus 10, by the way, it differentiates to 0. That's why I haven't written anything after this. Minus 2, lots of minus 2, e to the 4 minus 2 squared, which implies that at x equals 2 dy by dx equals 4 lots of e to the 0, which is just 1. So we've got the gradient. So now we need a y coordinate as well for the straight line formula to work. But remember, also, it asks for the equation of the normal, not the tangent. So actually, let's conclude, therefore, grad of normal equals minus 1/4. So now let's find the y coordinate. X equaling minus 2 implies that y equals e to the 4 minus 4 minus 10, i.e. e to the 0, which is 1 minus 10, which is minus 9. So we've got everything we need now to find the equation of the normal. So we've got y minus y1, so the y coordinate's minus 9, equals gradient x minus the x coordinate, that'll move up here, which implies that y plus 9 equals minus 1/4 x plus 2. Always good practice to tidy it up before we do any maths. And we'll write in a format that's friendly for fractions here. So if I times both sides by 4, 4y plus 36 equals, and if I multiply by 4, that disappears, just leaving a minus 1 outside the bracket, minus x minus 2, which implies that x plus 4y plus 38 equals 0. And there's the answer. Now, any 3-term format would be acceptable here. So you could do, if you wanted, y equals mx plus c. So when it's not given what form it wants, the question in, the answer in rather, then any 3-term format is fine. So often you wouldn't get marks for leaving it like that. Occasionally I get lenient and give you marks for that, but 3-term format like that there is necessary on most exam boards in most questions to get the marks. We'll not do the second part because it's more of the same. What I want to do now is have a look at some trig differentiation using the formula booklet. So I'll just get the question ready. So here's the formula booklet entry for differentiation. We saw it before. Let's keep that to hand and let's have a look at some trig functions. So I'll just get some ready. And again, we'll prove why these are the differentials when we've done the product and quotient rule for differentiation, which is next week. But for now, let's just take for granted that we're given these tables and that we've got to use them. So from this first one, I don't know why it seems awkward that they put a k in there, but what that's telling us is that tan x differentiates to sec squared x. So differentiate with respect to t. As soon as you see something like this, you should turn straight to your formula booklet to see if you're given anything. That'll help you do them. So cot of 2t. Well, that is a function, 2t wrapped in another function. So the chain rule applies. And we can see that cot differentiates to minus cos x squared. So let's not look in the bracket. Just cot of a bracket differentiates to minus cos x squared of whatever's in that bracket. We haven't looked in the bracket yet. Let's take a look in the bracket. We see there's 2t, and we times by the differential. Equals minus 2 cos x squared 2t. And that's that. Part B, sec of t plus 2. Let's make that bigger so I've got more room to space it out. So sec differentiates to sec tan. So sec x to sec x tan x. So let's not look in the bracket. We just see sec of something that we need to differentiate. So that becomes sec of whatever's in the bracket tan of whatever's in the bracket. And let's look inside the bracket. We see it's t plus 2 times by the differential, which in this case is just 1. So we're actually done. I'm not going to bother writing the times 1. Have a go at the other two. I'll give you 30 seconds to do those. But again, it's encouraged that you use the formula sheet. You don't need to remember the differential of these. So tan differentiates to sec squared as we established before. So sec squared of whatever's in the bracket. Let's look inside the bracket now and times by the differential, which is 4. So equals 4 sec squared 4t minus 3. And part D, cosec, you can see here, differentiates to minus cosec cot. So minus cosec, whatever's in the bracket, cot, whatever's in the bracket. Let's look in the bracket. We're out of room here. Let's look in the bracket and times by the differential, which means that there's a minus 3 at the front. Minus 3 cosec 3t, cot 3t. So just a couple of more examples before we're finished, because when we're working with trig, it can be quite confusing. So if I asked you to differentiate sine squared x. Now, we're falling victim to some poor notation here. Sine squared x, I personally think is an awful way to write sine x times sine x. Even though it's the accepted convention, I think it's an awful convention. I would prefer to see it written as this here, sine of x squared. And that makes it more obvious how we differentiate that, because we've got a function, sine x, wrapped inside another function, squared. So we know bracket squared differentiates to 2 bracket to the power of 1. Let's look inside and see that it was sine x and times by its differential, which is cos x, equals 2 sine x cos x, which just as a point of interest, you should recognize as being sine 2x. Don't need to simplify it like that. It hasn't asked us to. But that's it, just a point of interest. So d dx, let's say cosec to the power of 10 of x. Try that one. Take 30 seconds. Again, noting the poor notation, you probably should rewrite it in what I deem to be a nicer way. So a bracket to the power 10 differentiates a 10 bracket to the power of 9. Look inside the bracket, times by its differential, which on the formula sheet, you can see the differential of cosec x is minus cosec x cot x. So, tidying it up a bit, minus to the front, minus 10, and we've got a chain of 10 cosec x's. Multiplied by each other. And I've gone back to the awful notation simply because that's what's accepted in maths. Like that. So basically, that's everything. That's everything you need to know about the chain rule. So the worksheets that I've put online are very, very good for practicing this. So you'll see them in the live lesson area. So that's where we'll finish. So plenty to have a look at. So well done, brilliant. And I will see you next time.